Twirl.
Oh. I mean, I was there last time. I didn't ask anything. I still got a good grade. So.
But I think it's like he doesn't expect you to do anything. Just
I mean, if you're there, you guys can. Alright.
how is it? Because
What was it? Stochastic study in
Okay, we're down to the last piece of paper on the wall over there, and that's coming in the middle of this lecture today. It's weird vector called the eccentricity vector. But before we do that, I want to use what we did in the last lecture in the geometry of hyperbolas to do Rutherford scattering. And a couple of neat ways to look at that, and also lots of animations that go with it, and related scattering problems. So we'll do that, and we'll then come to this really elegant way of treating Coulomb fields and Coulomb quantum mechanics, as well as the classical. Then another way, still yet another way, a third way, to parameterize Coulomb orbits. And we'll also be seeing, when we do this, a geometrical construction, which I will not require you to do, but you can sit and watch it and play with it if you want to on your own time, that shows the momentum doing its really strange, they call it holographic motion, in which it traces a circle, but not a centered circle. Okay, so basic idea is that Rutherford changed the whole way of looking at physics that was in place in the 1800s and early 20th century by doing this shining. He didn't shine, but he held up to a gold foil an alpha emitter that gave off alpha particles, and that is a problem at the end of the homework today that I want you to take a look at, just to get the numbers and see what he did. How close did he really get to touching the nucleus is a question I'm going to ask. But the answer is more academic than anything at this point for him, because people thought that the positive charge was just as big a ball as the negative charge, and he showed that it was at least 1,000 or more times smaller. And of course we now know it's 100,000 times smaller. So the construction that I'm about to show you here is just based on taking an ordinary hyperbola and just turning on its side so one of the asymptotes can represent the beam that would be coming in if he was doing an experiment with some sort of cyclotron or synchrotron device. So the idea is an alpha particle is going to come cruising down here, and if the nucleus isn't there, it's just going to go on this line forever. But here we're talking about a positive nucleus, and it's right here. It is going to be already above the line when it shows up on the scene because of that nucleus, but the hyperbola is asymptotically attached as we go back in time, and then asymptotically attached to a scattering line, which is the other asymptote on the way out. So the idea is, how do you construct this? How do you make this a construction de novo? Say you're teaching it to somebody that doesn't want to look at all the geometry you've looked at already, and also hasn't heard this formula. That's the key to this, that the total energy of the Coulomb orbits depends on just one Cartesian parameter, the major radius, actually the major diameter, because it's the diameter that's sitting in the denominator of this expression involving the Coulomb constant, K over 2A, where A is the radius of a circle. You can imagine that this thing would hit and bounce off if it was dead on. If the B for beam impact parameter, the other radius of the hyperbola, the minor radius you might say, but usually it's bigger than A, so we don't use that major-minor distinction. Any B greater than 0 or any less than 0 is going to send a particle off in some scattering angle, and that's what we're trying to construct here. And the idea is really quite simple, and that is pick an impact parameter and go for it. Draw a circle just like the one that kept the thing, or tracked the turnaround that was 180 degree scattering, back scattering, and put it up so it sits right on above the original circle here, and then it's with these lines that we will get everything that has to do with that particular impact parameter. So the next step here is to copy this angle right here. Now I'm already giving it a notation phi, and I've done the same with your homework. It makes it a lot easier using the graph paper that has a protractor that's centered around the nucleus. All of the other lines here miss the nucleus. The double angle right here goes through there, and then the same thing would be true for the forward scattering angle, theta, and we'll relate those to backward and forward in just a couple of slides here. But this is where you get the scattering angle, however you label it, simply by copying this little angle right here up here and drawing a line. Okay, you might as well draw it down here if you want to keep the diagram symmetric, but keeping it as simple as possible right now. Okay, and so what you then will do is take a compass and strike an arc through the nucleus and come around and find where the second focus is, because that's that one right there is needed in order to construct the orbit, and we'll go through that in just a minute or two here. So that gives you then, well, first of all, the closest approach to the nucleus is right here. The slowest speed that it ever goes is right here. Then it picks up speed again because this is repulsive. And then, as I point out in the problem set here, if the anti-alpha particle were being shot from the other direction, it would be attracted to this nucleus, and it would follow a hyperbole using this focal point. That's kind of an interesting thing. It would come out with essentially the same angle as this one. So you're solving two problems, very different physical problems, with one swipe here. Okay, see if there's anything else I need to say. So we're going to have a forward, I guess that's to call this the forward scattering angle, but isn't really, what's forward and backward depends on where you throw the particle, how far your impact parameter is. Anyway, there's the phi, F for forward, and then there's the theta, which we call the backward angle. Okay, so there's an angle here that is indicated by combining these two for that dashed line right there. That is the outgoing asymptote. Particle eventually will be following it, but the radius from this point right here, the r of the polar coordinates used to describe these orbits, is that green line there. In any case, the asymptotes stand still, they don't change. This is going to keep going until finally this line will be parallel to that one, or very nearly so. So, the idea is that we have supplementary angle here, phi and theta, that is, they differ by pi. And we're interested in half angles. That's something you could read off directly with that protractor thing quite nicely. You can go ahead and read the double angle too, if it's phi, because it is using a line that goes through the nucleus. All right, so that's basically the construction right there. Except that we haven't gotten the actual curve yet, but we'll do that in a minute here. Just want to point out, there's a simple little triangle relationship between these two. If the angles are supplementary, then the half angles are complementary. That is 90 degrees over 2 is the difference for that. So you have a little right triangle consisting of the impact parameter and then the energy parameter, the thing that goes in k over 2a. There's 2a, that's our closest approach that any of the alpha particles are going to get in the beam that's supposedly coming through here. So, if you go for a larger B parameter, like 3/2, and I'm asking you to do 1, 2, and 4 actually on that first problem, a revised version of it, which you should look at, not the old one. It's a little confusing to what I had left in there. Okay, but in any case, now what we're seeing is the half angle when double takes us here. So now the particle's going up northeast there instead of northwest. Now all of this is symmetric. I flip it over, does the same thing below the beam axis. Now at this point we make use of the thing that every high school student that can pass a hyperbola exam knows, and that is the difference between the R that is measured from the, in this case, the nucleus, and the R prime that's measured from a point that has nothing at all physical there. It's a mathematical point out in space here. The secondary focus, okay, has a radius R prime, and then the radius right here, R, is from the first, the prime focus, you might call it. I will get in trouble with the notation here because this thing has a prime on it. It's not what I mean by prime. This is the first focus, that's the second focus. Okay. So, and there's the right triangle that's got A and B on the thing. So it's a, you know, it's a very elegant construction. If I may say so, because I hadn't seen it anywhere, so I sent it to American Journal of Physics, and it appeared without any arguments. One of the few papers that just sailed through without an argument. But in any case, the idea is that the difference between R prime and R, that's this distance here, subtracted from 2A, okay, that's what we're doing. We're getting the R prime to be equal to R minus 2A, 2A right there. That's what we need to do. So whatever R we get, we strike that arc over to here, and then we simply set our compass to the R prime that's right here, take that up, and strike an arc. And where it hits the circle that we drew with the R, and now we know what the R prime thing is. We don't have to draw a whole circle for it. Just go and touch one there and touch one there. So there are 2 points on the hyperbola that's going to go cruising through here, just like this one. But this one's going to end up over there, as we have already seen. Okay, so that's pretty simple, right? Very a nice way to visualize these things. So just just keep making random choices for R wherever you want to pick a R, or you could do it by picking R prime and going backwards here. You get more and more points on the hyperbola, right? Now it's kind of tough to get it just right, so you get points in here, but that's a curve that we can sort of figure out. We know it's got to go through there, so it's not too hard. Particularly if you're doing this construction on a computer, if you're trying to make diagrams using a drawing program, you really don't need very many points. In fact,
That's
the
why not.
Bezier curves are so good now that I can just touch here and just kind of guess where the hyperbola is going to be, you know, come out and stop, and then I get a whole bunch of adjustments that I can make. So I would fit this point, say that point, and that one I have something that's within a width of a line for the trajectory. Okay. And of course you just forget about all of this and just program the darn thing, and we'll be doing a lot of that. Because we like to do hundreds of these curves in order to see what's going on here. So what we're talking about for some of the examples that are coming up here, and by the way, that's a very important formula right there. Either one of these, okay, they're inverse of each other. Oops. This one should be cotangent. I believe I'm wrong. This one should be tangent, that one should be cotangent, so that's a mistake. I just put that in today and I didn't correct it. So check that one. Okay, so here's an easy way to do it. Go get our program for Coulomb things. It's called Coulomb Web, and let her rip and see a whole bunch of trajectories all at once. This is really quite amazing. You see the result down there, and so I'm going to go ahead on this computer here, which I think is the best one to try this, and let's see. So once again, I've forgotten to run this one through its courses, so let's hope it can pick this up. But it's the one that's usually pretty well behaved. So let me see if I can get this to go, to see this in motion. And by the way, before we run it, let me explain the rainbow. Remember when we were talking about the Lagrangian of a classical trajectory that you get just by integrating p times velocity minus the Hamiltonian, which is constant, okay? Just by doing that and then coloring it modulo some number, that's what you get by just clicking here. You actually get a look at what the quantum waves that would be for this scattering if you chose the h-bar and energies and momentum correctly. So this is a wave here. It has a wavelength about this long, red to red, okay? And that is what you're going to see in the movie that results from, we hope, activating this particular thing. So let's see if we can get it to go here. And there she comes. Okay. So there are the alpha particles. Now what's amazing is if we start them anywhere down the line, it's a straight line just by setting initial conditions. And that straight line doesn't bend very much until just about when we reach 2A. Isn't that wild? Who would have thunk that? And now some of them are actually starting to come back on the trajectories that we would have calculated with a ruler and compass. And the contact point is being respected, you see, and out they come, okay? That's pretty neat. Now I'm going to go ahead and let it finish. Just resume. I think it will keep going, okay? So eventually everything is off screen, and the scattering for this little box is finished, okay? Now, what's really quite remarkable, I think, is if you take a compass to this diagram at the middle point here, the center is here, not where the nucleus is, but it's creeping. It's creeping, and we're going to talk about that. It's very creepy. Okay, this is logarithmic effects that Coulomb does. Okay, so it has to get way out there. It still never quite gets there, but it gets within a pixel after the wave has gotten to Springdale or someplace. Okay, it's really quite amazing arithmetic that we're going to see, and that's part of this new Unit 6 that you already have. So some of this is in the very beginning of that. Okay, let me bring this thing back to the living here, so we can continue the theoretical descriptions. Now, to analyze the envelope for this is not a trivial problem, but the hints that I give in there and these pictures should be enough for you to do it. And it's based on our old friend, the parabolic kite, whose center line, you see, is a tangent. Okay, so the center line of the kite is pointing to a contact point. And that contact point is what we're looking for. We're looking for that wonderful point where the parabola, which is right here, touches a particular orbit that has some value of b. Okay, and that is an orbit that comes up and contacts the closest approach point, and that's what we're looking at right here, the closest approach point right about there, and then goes on to have another contact at the end of the kite. So the question is, how do you draw the kite? Okay, how do you locate that? You see. And one of the things that I harped about when we were doing the idea of the, well, it was the volcanoes of Io was one problem. And then there's a problem that is less astronomical, more atomic, involves the National Institute of Standards and Technology making a fountain, which Junyi tells me is still the way they keep time, even though he's gone on and improved the accuracy by almost 1 billion-fold. Still, the time that you base your thing, you don't need to know it to 19 figures, so no loss for most of our lives. But in any case, the idea is that this tiny little fountain is analogous in this sense of classical orbits to the very classical volcanoes of Io. Well, so is this. This has a giant that goes with it that's really amazing. And that is that this picture here could be the picture that we see, in fact, we do see. Darrell Judge, who's recently passed away, USC, was one of the first to study the Mars Rangers readings on Lyman alpha spectra, and what he discovered was that the solar wind, which is a Coulomb field, it's a Coulomb field for light, goes off as 1 over r squared, the force. It's a Coulomb field for protons, meson, you name it. There are, because of our motion through the galaxy, here's the sun, here's the Earth, Mars is somewhere right about here. The Mariner passed through the bow wave of the sun that is associated with Lyman alpha resonances of hydrogen in the galactic space. More or less, more stationary with respect to the galaxy than us, leaving this wake. Isn't that amazing? And that thing has been mapped piece by piece, a little point on that thing every time we send a spacecraft out past Mars. It's that often, right? It's going to be less often if we go on an anti-science kick for a while. In any case, there's the giant associated analogy to Rutherford scattering. But as I pointed out to you with volcanoes of Io, was that a contact point has to be on a line with the two foci, one of the foci associated with the thing that's actually orbiting, and the other foci associated with some sort of thing that's standing still. And that's what we've got here. And basically the idea is that these guys right here line up with the relationship 2a r minus r prime. That's 2a right there. Remember, that's a copy of the closest approach. So you do a copy of the closest approach to get the directrix of the parabola, and then of course you can think of the parabola's other focus being at infinity, but you don't have to think about it. You just stop right there and draw a line. If you're interested in this particular orbit right here, if that's the B value, you draw a line through that, and then there's the 2 times B is right here. So you get this guy right here, but you also want to draw a line to where this circle intersects the incoming asymptote. And that will put a point right here. And that will point through those 2 things at this, and all you have to know is some other line that crosses that. And what the other line is it's perpendicular to this. There's the kite. You see right there. So you have to let the kite point to that horizontal line, and there's your contact right there. Okay? Well, it took me a while to discover that one. But I'm asking you to sort of play with it a little bit in the second part of that Rutherford problem. Okay. And I've included here in the lecture a couple more pictures of that whole thing. The idea being this applies to each point on the upper hyperbola. And then I'm asking you also, at least in the beginning of the thing, go ahead and show the attractive one. So this is where you come pretty much to get the information for this thing. Just today I went ahead and used the compass that's that comes with this problem, and if you want to pick up extra copies, I advise you to do that, because it's obviously some things they're going to have to be erased as you try this out. This is a particular example for b equals 3. Okay? In other words, I'm asking for the arc tangent here. I wrote down the wrong page. That's the cotangent. The arc tangent of 3 over 1. That's 71.57. If I could do 4-figure geometry, I should see that right on this line. This is the half angle. Okay? There's 70 degrees, 0.1, and then it's even a little bit right of center. Yeah. It's not 0.5 exactly, according to the way this came out. Now, I did this before I calculated that, so I am really amazed that I got that close. That's really pretty damn close to 71.6. But no way you're going to get 4 figures, right? There's 10 pixels just in one of these divisions here. I could do it, but I don't have that many pixels on my pencil. Certainly not. But on a computer, when you do stuff like this, you can do geometry on a computer. Great accuracy using a retina screen, right? You'd be able to go easily 4 figures, maybe 5. Okay, so good lesson. All right. So that's the geometry, and then you've got a funny kite like this at the low B. That's really, here's a square example. I'll zip by that right now, but I'm asking you to do one like that. And also answer the question, what impact parameter do you need to have a particle go straight on? Okay. Let's see if there's anything else here. Yeah. Now, just quickly, as I said, this is an approximate model for deep space H-atom scattering solar wind. Okay. Sun travels around the galaxy. We're not going to live long enough to see it go very far. It's a whole long time to go around that galaxy. But we're cruising. This shows we're cruising. Okay. It's really amazing. Called the Lambda alpha shock wave, just inside the Mars orbital radius, 1.2 atomic units. In any case, what we are lucky to have Rutherford do early on is the idea of the scattering cross-section and a solid angle. Now, you're not going to make a big fuss about this. You can read this on your own. Here I'm just working out the differential scattering cross-section that is sort of on the cover of the mechanics book. It's so important. You have a certain differential beam impact parameter, and all the particles go through this little window here, and it has a differential phi angle azimuth around the center of the beam. Okay, but all the particles go through this thing, do a little flip-de-doo, and end up going out on an ever-widening d theta angle, solid angle in polar coordinates. And that's a weird mapping, and you have to use the Jacobian basically to figure that out. But you know how to do that already, even if you didn't take this course. I think you can see what we get. And this derivative of b with respect to theta, which is something we can calculate pretty easily. Now I've got the right formula there, b equal a cotangent of theta over 2 is what makes this thing an easy algebra problem. So we get the Rutherford differential scattering cross-section. At first it looks like a big mess, but with the half angles it's not so bad. It just turns out to be inverse sine force power. And that's what he measured. And everybody said, that's crazy. That means you're scattering off a tiny point. Yeah, that's what it means. And that's what atomic physics started. I now knew the nucleus was something very special and small. Didn't really know how small, as you'll see by putting the numbers in for the contacts. Okay, now let me point out that the Coulomb field in general is referred to as a logarithmic singularity. That is, if I try to get the total cross-section from that darn thing, well, sine minus 4 just blows up. That's infinite. And you can see why. This parabola just is wider and wider and wider and keeps going. If this was the only game in town, if it was just that nucleus and the alpha particle, it's infinite. But of course it isn't. The atom has its electronic screening going on at a great distance compared to what we're talking about for Rutherford. So somewhere out in the parking lots, we begin to see some electronics stuff that actually is a little bit attractive to the alpha coming in. Okay? But the electron is much lighter than the alpha. There isn't really much of a scattering. So we can imagine that Rutherford's results are good because the electrons really didn't do much to the thing. But it does take it down to the point where the very fine stuff that happens, that we'll talk about, the logarithmic stuff that we'll talk about later, gets washed out in that particular place. And if you go ahead and use this formula for the angles that are scattered off of just a ball with BBs being shot at it, and they're all doing angle of incidence equal angle of reflection. I used to give this as an exam problem, or qualifying exam problem even. The hard sphere scattering here, you can integrate the thing, and you'd better get the cross-section area 2 pi r squared, right? Okay, good. Well, this is the thing that I really am humbled and proud to work on, and again send into the American Journal of Physics and Habits with a little bit of argument sail through. And that is, how do you do the geometry of the eccentricity vector? First of all, naming a vector that has a lot of names on it. The A vector with Km on epsilon, okay? And you remember that sort of Km thing in products gives you an angular momentum parameter in our little parameter box. This is known as Laplace, Hamilton, Gibbs, Runge, Lenz, and I'm told that Pauli also got his name on this thing. Okay, so just about everybody's got their name on A. I haven't been gross enough to put my name on epsilon, but if I was, you know, like Trump, I would put it on there and make a neon sign showing it with gold, LeMay. The thing that's interesting about this, though, that I find is that the epsilon is more like the Stokes vector for the oscillator. Remember, we're comparing Coulomb and oscillator here. These are our A, B, and C components that describe an orbit, a polarization, stuff that we did in Unit 4. So this is analogous to that. It is a description and helps you with the geometry, just like this does, of the actual motion that goes there. And also, it's part of a symmetry group this, the A here, actually put that there, most of the time you use the units, so that when you take a commutation of the A vectors, you get angular momentum. You take angular momentum with the A vectors, and you get A vectors and J vectors, depending on what products you take. And that's the group R3 cross R3. That's the rotation group in three-dimensional twice. There's an inside and an outside to it. That's really spooky. But that is a subgroup of O4, orthogonal group in 4 dimensions. And R4 as well. It actually is R4. Okay, so that's the group theoretical stuff. And by the way, the next course I teach will be on molecular physics, in particular a lot of this stuff, atomic and molecular stuff. So if you like this course, that's where this continues. And I'd be glad to have you guys, any of you guys, to take that. It won't be an intensive course with lots of homework, so don't be afraid of it for that reason. But there's a chance to learn some really cool stuff that, well, nobody knows. And Jun Yi has, keep this quiet, worked on getting spectra of this thing called buckyball, and that's this guy. And so we're going to work on that one a little bit. And that can be fun. There's just all kinds of weird stuff that thing does. But in any case, this is the best proof I can give to you that this is a useful vector. First of all, that it is the eccentricity and that it points on the major axis of the conic section. It doesn't matter which one of the conic sections. This one takes care of them all, and all the physics goes with it. So it really is a powerful thing when used geometrically as well as algebraically. So what I'm doing here, this is a unit vector R, that's fat R over the size of the radius, and then there's this P cross L, that's P cross L cross the L right there, R cross P, okay? Which I immediately turn around here, so that I get R cross P dot L, that's just L dot L. Okay, so this is, you know, pretty simple expression for the eccentricity dotted with R. Okay, by itself it's kind of mysterious, but this begins to take the mystery out of it, particularly if you just do L squared there. Okay. Now, I should also point out that with momentum it does something weird, and we'll talk about that later. And I just noticed I forgot to get the hat that's turned into some Hebrew symbol with these new fonts. Which, by the way, did you notice that the font box in any of the Mac computers, and it may be true of the PCs, has left out epsilon? The Greek alphabet does not have epsilon anymore. They have uppercase epsilon, big E. They don't have the lowercase one. What the hell is that about? Anyway, that's just on the side here. That's why we're having all these problems, because they screwed the pooch. Poop the pooch, I guess.
Do a text search for the word epsilon.
I did.
Oh.
No luck.
No.
It's, you know, that means the fraternity sigma alpha epsilon is going to have to be sigma alpha delta or something like that, sad, instead of SAE, right? And it is pretty sad, so that'll make sense, actually. Anyway, this is PR. We'll get to that, although it's not terribly important, but it is something else to notice. Anyway, this is epsilon r cosine phi, right? You see what I'm getting at? You remember our equation for the orbit of an ellipse or any of the conics? There it is. Proof. QED. This beats the heck out of the, you know, what Pauli went through a whole bunch of commutation to show that the A did its thing, but the epsilon immediately does something for us as far as the geometry goes. So, remember our favorite quantity for the Greek angular momentum thing, Melly, is the good old lambda here, the lattice radius, okay? Okay. This matches this perfectly. This is apogee, zenith, and perigee, if you want to call this the zenith. You're standing on this thing looking that way is up. Okay? So you have perihelion, aphelion, then you have perigee and apogee. Okay? it should be called the uphealing, don't you think? And the upogee, because it's the high point. Pair means, I don't know, the opposite, whatever. Okay, you get funny with this stuff. Anyway, that's the idea, and of course that was the first thing we were looking at, using the lambda to write algebraic expressions. So we just bypass all that stuff we did in the last lecture, but not quite. There's things we learned back there that are still interesting. Okay? So if you have an attractive, and for us that's k greater than 0, remember that little sort of rule that I picked, and then if it's an elliptic orbit, that is, if it's energy less than 0, this is what you're dealing with, okay? The rotational momentum L r cross p, of course, is normal to this thing, and then when you cross it with p, you get the p cross L we have in this thing right here. So that's where I'm getting the epsilon, okay? I'm adding the unit r, okay, with the p cross L divided by a coefficient that involves the coupling constant. So, this is an attractive for center. That's where the attractor is, whatever it might be. If it's a mass of some kind, a planet. And then there's nothing here. The second focus is just for fun, okay? Well, we need it, but it's certainly not anything physical until you get deeply into this thing. Just the opposite. If with an attractive k greater than 0, you go up in energy above 0, make it positive, okay? If you make it positive, you're going to have a hyperbola. You can see that because now p cross L points this way, and this is the attractive center now. This is a nothing, okay? Until you change the sign, and then it's a something, and that's a nothing. So this, having two foci is a little annoying sometimes. And finally, the third case is repulsive, and there's nothing you can do there but get hyperbolas. So now the nothing here, and there's the repulsive thing right there. So that's a sort of in a nutshell what all of the geometry we're going to do for the rest of this lecture is based on that. We'll mostly consider this case, but these are fair game as well. No more difficult than doing this case. So, boy, I really give credit to all these guys, okay? And then Mr. Epsilon, too, right? Okay, now, here's this great big pile of formulas of the geometry that we did before, and it won't hurt if we bring things into order here. I'm going to jump ahead here to this guy, and then we're going to explore a little bit of this geometry with the epsilon vector, showing some of the things it does. But here's the physics right here, okay? The km lambda, right, is our angular momentum. That's L now. We're not going to use mu anymore. And then here's the impact parameter, which is proportional to L, but it's also inversely proportional to energy, square root of it, with a mass of 2 put in there. So as I said, all of these are, if we were doing stuff old school now, these are guys that would have to go in your permanent memory in order to get into the exam and pass it, right? This is kind of it. And when you're doing homework, look at this first, and then you can look at the other stuff later, right? Okay. Anyway, let's go ahead and just see what, if I carefully graphed out an ellipse that has an eccentricity of the square root of 3/2. I expect that because it looked nice. 0.866. And let's make use of the other scalar product. Epsilon can be product of momentum to some help. It helps us to see that. It says it's epsilon times, basically what we're getting out of this thing is epsilon times p. Now epsilon, as we found out, is pointing on the x. When I dot p with epsilon, I'm taking the x component of p in that product. So And then this thing right here is P dot R unit, so that really is the R component of P. So this is saying that the projection of PR, that is the radial component of P, projected onto the radial R, or R prime, doesn't matter which one of those you use, this is the R, that's the R prime, okay? This is going to be equal to the eccentricity epsilon times the projection of Px. That's the projection Px, the x component of P, major axis. All right, so that's what we see. There's the Px and the projection of that onto the radius. That's the equation that I'm talking about that we're getting here. That gets useful later. I'm going to rush past showing that for different places. There they all are. The problem with this was the lengths of the P and minus P are not drawn correctly because momentum will be growing like mad as I get it. We're going to see that in another construction depending on how far you fall toward the attractive center. So page 85, which is coming up fairly quickly here, is where we'll do that. It'll also be interesting to see what it does right at the lattice radius point. But one of the other things that comes up here, and this is what really this showed, was that any time you draw the angle that I'm talking about here between the radius that we normally are used to using and this secondary radius, it has a use, okay? And the bisector here is normal to the tangent vectors, that is normal to the momentum. That's cool. You can use that. So really that's what this little thing told me right away. Anywhere you go, that's going to happen. Okay, that's neat. And it also happens with hyperbolas. Okay, here's a hyperbola right here. I got an R and an R prime. I bisect the angle between those two lines, and there's where my momentum's going to be. The question is, how long is that momentum? See, but at least I know where unit momentum is. Okay. Now let's take a couple of minutes here just to go through a construction which, using the epsilon vector, derives all possible orbits. We're just going to lay them out here on one piece of paper and have a good physical intuition added to our repertoire of understanding. Okay? So we're going to start off given some initial momentum. You know, just pick it out of the blue. Just draw a line along which the momentum will be. Not even necessarily specifying whether I want to go this way or launch it like it was a globe ballistic missile. I'm playing Rocket Man now, okay? Either one of those two will lead an orbit. Presumably, if I launch this thing far enough, it might go, way out here, and then hit somewhere here. But if this here isn't here, if we're actually looking at a very dense thing right here, continue on its way and come in this way. So that would be the use of that vector right there, just a minus of what we shot. All of that's going to come out in a nice way here. I'm going to be able to tell you various things about the orbit and pick different parameters. We're going to have an energy scale. It's kind of weird. That's this thing. But anyway, this is the construction. It's basically 3 steps to develop a little slide rule that lets you get all the possible orbits. And remember, we start with attractive, okay, so we start with ellipses, then we crank up the momentum more, and finally we're going to reach escape velocity, and after that we'll be drawing pictures of hyperbolas emanating from this thing, something that you really throw it fast, it's just going to go straight, and then start to bend a little bit and be part of a hyperbola. The middle of that is a parabola. We got to find out where that is. That's that weird case where you have exactly 0 energy. Okay, now let's go ahead and state the thing. You pick a launch point. That's the radius vector. Okay, so you can have that anywhere you want. You draw a circle just to indicate it might be a globe that you're launching from. And then you have an elevation angle. Okay, elevation from the R. All right, gamma. And I maybe should have picked a different letter for that, but it's what I'm stuck with. I haven't seen any reason to change it. We don't have any Euler angles here to make a mess of it. So we're in good shape. So here's what you start with, okay? And then you draw a circle, just like the main one, around that, and copy the angle, gamma. Kind of like what we did with the Rutherford scattering. This is a half of an angle we're interested in, this gamma. But it's a good parameter by itself, as we'll see later. Now, by doing that, you have produced what I call the focus locus. The focus that you're looking for this orbit that you already stated has a certain angle of launch is right there. Okay, how is that possible? Well, the idea, you see, is that when focus has to be that place where you put the string for the orbit, and you're starting here. Okay, so there's a string coming up like this and a string coming here. But the basic idea is that this thing reflects off the P line and goes right to there. So that's what a focus is supposed to do. Whatever comes from this focus has got to go up and reflect. Well, that's our momentum line, our initial momentum, and go down that line. Okay? So that's what happened by doing that copying step right there. And this is just saying it again. Line R from first focus reflects, quotes, off the line P, that's the momentum line, toward the second focus, F prime. So I can go back here. I go up here, reflect off it, and my F prime has got to be somewhere here, or here it turns out. It can be on either side. That's going to be what makes this construction powerful. Okay? So then the final step here to set up the slide rule is copy the double angle again. That's one way to do it. It's not the only way to do it. But basically what we're going to do by copying that double angle again is get a perpendicular to the reflection line. In other words, split the difference between that reflection. Okay? And then wherever that hits this circle that we started with, that's our ratio scale. It's the ratio of kinetic energy to potential energy. I'm just telling you that. We'll prove that by more detailed looking at this geometry, but that's it. We're done. Okay, so if I've got a -1/4 ratio between potential and kinetic, and that means basically, since the kinetic energy is a velocity squared, right, potential energy here, if I take the square root of that, I'm getting what fraction of the escape velocity I am at by knowing this ratio. Okay. Now, that's what I'm really saying right here. It's initial KE, that's V squared over 2, initial PE minus K over R. Remember, I have to put a minus on this thing. And whether K is positive or negative, it's still going to work. Okay, so that's initial velocity over escape velocity squared. That's what this ratio is. Pretty cool. Okay, so it's a very useful ratio, but it's also geometrically convenient. All right. So once you've done that thing, just point the vector at whatever value of that ratio you want. You see, and you have quite a range. You can go up here and pick some stuff. Or you can go down here, or you can go down here to this point right here, where R is -1, the ratio is -1. So the only hard part of this is you've got to make a scale. You've got to mark off a scale here, 1 to 10 or something like that, or in quarters like that one is done. So for example, if I point at 3/8, that's my eccentricity vector right there. Wow. And the eccentricity vector obviously has the foci. So the foci will be out there at the focus locus. Isn't that cool? It's really slick. You can almost remember it now, right? Okay, I'm taking this all down, we're having a quick exam. Right, yeah. There's remembering it and there's remembering it, right? Okay, so we'll skip the exam, just kidding. But that's the second focus allows a construction right away. Now that I have the second focus, I can make sure that the sum of these two things add up to what the sum of it was. So I string this thing up here, that's a 2A, and I cut pieces out of it. And just like we made the orbit of the hyperbola, we make an ellipse orbit pretty quickly. So that's it. That's worth a paper in American Journal of Physics. And pretty low argument of value. Now, if you swing that guy up into this region, this is the region where E is greater than 0 and K less than 0. Okay, so this is a repulsive orbit that you're making now. Okay, so when you should put the focus up there. Okay, and here's your initial velocity. That could be your initial velocity, or you can go this way. Okay, and you go one way and you don't get this way because these orbits are not coming back. They're hyperbolas. They don't turn the corner and come back. But so you have to redraw the thing over here and there if you're doing it on a computer. But you see the various regions of this thing, particularly the focus locus that you would be getting by pointing a vector beyond this point right here. You see. So if I have an epsilon vector that is touching right there, well, it's parallel to focus locus, so I don't get a second focus, right? There's my epsilon pointing at the other focus, but there isn't one nearby. It's an infinity. Or it's way the heck up here, you see. Just go a little bit, one side or the other. That's what I'm doing, and I haven't. The orbit is still an attractive orbit, but I'm above escape velocities for everything here, for sure. And as I start to swing the thing, down there, that's when we get our other kinds of hyperbolas. Okay. I'm going to go through the proof of this thing now. Let's pull this up. So it's in position to go step by step. Already said these things. Basically, we're talking here about the basic definition of the epsilon vector, which consists of a product of momentum and right here, MVRO sine gamma. Okay, so these are components, basically angular momentum. All right. So this is what it boils down to. It's 2 sine gamma, okay? That's the angle we chose, the elevation angle, okay? KE over PE, okay? That's that thing there. And then a unit vector that points in the direction of the angular momentum, which is out of the screen, okay? Now, P cross L, on the other hand, is back in the screen. Okay, so it's the P cross L that we're drawing here, the 2 sine gamma of this thing to be added to the unit R that we already have. So this is the unit R, and then we're going to be tacking on to it the basically this quantity here that is perpendicular to both P, okay, that's, let's see if I got this right here. Yeah, that's this right here, the 2R sine gamma is right there. And we just checked that to see that that actually works. The eccentricity vector that consists of a cosine and a sine of gamma multiplied by whatever the epsilon is, and then a 2 sine gamma for this extra little guy here, and this is in a coordinate system riding with this, gives you this right here. So if you work that all out, for example, for R equal 1/2, that would be this one right here, or that's minus 1/2. Here would be plus 1/2, so this is what we're actually drawing there. this particular case right here has an epsilon vector. That's this whole thing here that is in the this particular coordinate system, 1 and 2 square roots of 2. So it's more of this stuff than that by a factor of 2. And eccentricity parameter, this guy right here, then follows fairly easily from this. But you've already got it. That's what it is right there, pointing at r equal a half. Come back down to here, okay, you have an eccentricity vector just at that point right there. That's a launch of, from, you know, with this angle right here. It would just take you up and back and down. That'd be completely, I mean, eccentricity vector, let's see if that's right. This is getting a little confused at this point for this extreme case. But let's see if I'm thinking of this thing right here. Eccentricity gets the smallest value right there, the least eccentric thing, which would be an ellipse that has is least long. If in fact you tilt the angle so that the scale comes all the way down here, then you get something with eccentricity 0. That's a circular orbit. So you see that one very easily. It's by swinging the thing around. So the eccentricity is a 0 vector. Well, anyway, all that aside, this particular, and let's try this particular thing. This is a simulation here of the building of an epsilon vector, and so this is going to be something TC is very proud of. That will show if it works. Let's just go ahead and see it. Yeah, there's showing also the P. We haven't gotten to that yet, but that is a part of this whole thing. And let's see if maybe I'm thinking of somewhere else where there's actually a movie where you make the let's go ahead on this one and see if I can find that. This one right here. This is the movie construction. Okay. So you try, he's just sort of trying various places for the placement of the thing and getting initial momentum there, and when you stop you get the orbit that goes with it. So here's where you, if you want to, just learn how to manipulate and actually draw an orbit on the screen there, and let me just see if I can, I guess that brings us back. But this one, I think I can probably do what it is. I'm going to just do a resume here. I'm going to reset, erase the paths, pause, erase the path, and see if I think I can remember how to do this. Set an initial, whoop,
Just click out away from the origin, then drag.
Click away
Yeah.
from the center. There we
There's
go.
what you're
Yeah. So
picking
there's
the
the
coordinates.
R scale right there. There's the initial momentum right there. And there's the focus. So I know what I'm going to get pretty much. I can guess what I'm going to get. I'm going to get an ellipse going through the initial momentum around. That's one focus. There's the other. Okay. Funs and games. Very nice animation as we take advantage not only of ancient geometry, but also all of this wonderful computing stuff that we have. Okay. We're sort of running out of time here. I would like to go ahead and there's that picture again. Here's where we actually figure out what the momentum does. And I would be very grateful if I could get a simpler derivation than this, but basically it's based on the angular momentum. And then I need to work it into the equations for the radius there. So basically I just put the r squared in from this one and go to work here, taking the time derivative of that so I can get an equation for that. It's very similar to what we had to do first when we did our algebra. Okay, so we can work those two against each other and end up here with something that looks like it's going to be a mess, but basically what we're asking here is for the Cartesian x and y, but also what we're going to be getting, this is the velocity x dot, okay, and the y dot right there, looking fairly complicated, but it isn't. Basically, those two cancel, and you get a sine and a cosine off-center. And that's exactly what momentum does, is it cycles a circle. So I'm going to show you that. This won't be an animation on the computer. This will just be one I did frame by frame with a ruler and compass, but on Keynote, so it wasn't actually poking holes in the screen. I was drawing circles with Keynote. So it starts off tiny little momentum out here, and it's already gained its length, and all of that is coming out of the R scale, okay, which it is there for a particular value. The kinetic energy, initial kinetic energy, is not something. The initial ratio Ke to P is not a constant. Okay, you can see the scale changing here. It's always between those parts that make the bisecting structure there. But by now the P has gotten really big. Okay, and that isn't half of what it gets. Now it's really showing. Here we're just at the lambda point. There's the lambda value. Now P is really big. Okay, so this gives you a feeling for what's going. Use the construction to get a P through the focus, and then I just bring it up to the top where it belongs, tangent to our particular moment at time. And it's pretty much as far as it's going to go. There it is at the end. Okay, so that gives you some feeling for this construction with momentum included. Okay, the whole thing is a package. A full phase space is obtained by eccentricity vectors. So that's a really important thing. Now, the rest of this you can read on your own time. This is where we use the ratio and the gamma as parameters. Okay, so it takes a little bit of work to get a formula for all of the parameters A and B in terms of those. Here's the lattice radiously similarly related. There's the B over A ratio related to the epsilon squared. So this lets you go back and forth between the parameters that we use in this epsilon construction and the others. And you see some interesting geometry in that too. Well, this is the end of the lecture, which has some more graph paper, and so be my guest to some paper that's sitting here on the desk, but also if you have to, you can get it off of the web. Okay? All right. We'll see you on Tuesday coming up.